Laplace used this on mu right here. Used proportional to 1 and used on phi the precision 1 over phi. And I don't know where he came up with 1 over phi. I haven't seen it in what I've read of his materials. It's hard to read through his stuff. But no explanation on how he got it, but he was using the reference prior. So you will hear people say that Laplace only knew about flat priors. It's not true. And so in some of his examples, he was using non-flat priors, so that's kind of cool. But it took a little while for people to figure out what this stuff is all about. You know, prior sounds a little bit bad. So it's like, oh, statistician that invokes their prior knowledge. For me, that's every statistician. That's everybody out there. I'm going to use knowledge about something. What are you talking about? I'm not allowed to use my knowledge to investigate anything. So that's not what they're saying. They're saying prior information about theta. You know, and some people say, well, what if I don't have prior information? And we're already learning lots of strategies where we can invoke our ignorance. And say, I just want to kind of model my ignorance. And this strategy right here that we're talking about is a pretty decent default strategy. There might be some better ones, but this is probably what most people default on. So most people end up using this Jeffreys stuff. So getting back to midterm, Monday, we'll talk about it. We'll lock down a date. So look at your calendars and be prepared. Okay, more Jeffreys. Okay, I'm going to try to go a little bit slower. Said a lot of things. I haven't done all the math, but we worked some examples where we at least know a Jeffreys prior is easy to compute. So nothing too challenging. Let's just think about a non-invariant prior rule. I've been talking about this, so just to give us some bearing, let's consider a problem that we know well. X comes from a normal, and we want to infer mu. And so a non-invariant prior rule says this. So experimenter 1, the non-invariant prior rule, I can come up with a lot of them, but here's my rule. Place uniform priors on whatever you like to think about. And so experimenter 1 likes to think about mu, and so follows the rule and invokes the prior of uniform. Experimenter 2 likes thinking about 1 over mu, the inverse mean, and follows the non-invariant rule and establishes this. Why I wrote that down. That this is proportional to 1. So that's the non-invariant rule. So they both write down uniform priors. These two scientists with the same data set and the same knowledge of the model will get two different answers. And so now it does depend on how much data they have, how far apart their answers are going to be, but different answers seems a little bit problematic. And so what I mean by this is if experimenter 1 transformed over to experimenter 2's space, they're not using the same prior. So if I just transform this, so my transform is just going to be mu is equal to 1 over psi right here. Same thing as psi is equal to 1 over mu. These are inverse functions. And then I just want to figure out, when I do this, I'm going to end up looking at pi psi. I'll just be real specific about the notation. This is going to be equal to pi mu when I plug in my what I want to call psi right here. So every time I see a mu, I plug in a 1 over psi. And then I end up taking this derivative of this inverse function. So this thing right here is 1, because that's what experimenter 1 was using. And this thing right here is 1 over psi squared. So that's what we had established last time. And so if you like this prior right here on mu, if you're being mathematically consistent, this is the prior that you like on psi. So these are equivalent to each other. They just look different, but they're exactly the same information. They contain volume in the space just the same way, just in a transformed way. And so these two experimenters aren't using the same prior beliefs. Now, what I established last time is that if you end up taking the information, take the half power, that these are going to be equivalent to each other. So this is an invariant rule, and we'll see that in just a second. So these have the same info. So what I mean is they're isomorphic, if you like that word. So they're the same. In some sense, they look different in terms of the letters and characters that I'm using, but they really are the same thing. So let's just try to understand why this is true again. So just remember when we do a transform, when we transform density functions, we do this. I'm going to end up looking at p phi, bless you. This is on phi right here. This is going to be p, I'll say theta, right here. And I'll plug in a theta, d theta, d phi. If you want me to write that differently, I can. So I'm just going to write down, this is g inverse phi. So g theta is phi in all of this. And that's just g inverse phi. So that's how we do transforms. So if I ask you to move to a different scale, this is the calculation that you have to do. And so we ended up saying this. This was our claim. We said we know a function that also does something quite a bit like this. And that's the information. So this is true. I theta 1/2 d theta d phi. I haven't proven it yet, but this has exactly the same form right here. So if I take that thing and I make it equal to that, and I take that and I make it equal to that, then they have this sort of functional relationship. So let's imagine experimenter 1 likes to talk about phi and it computes this right here. And experimenter 2 likes to talk about theta, computes this. If they want to talk to each other, they have to transform back and forth. And so because of this relationship, if they end up using this as their prior, it will auto-transform for them. It has all the right properties, that function. Has that scaling function built into it. And so that's all we're doing is we're just substituting this into this equation. We see the same form. So what this says is I choosing your prior proportional to I theta half is transform invariant. So if somebody was using this right here, let's imagine this is experimenter 2, and experimenter 1 did this right here. If experimenter 2 wanted to get experimenter 1's posterior, and they were both following this principle, experimenter 2 would take his thing and multiply it by this scaling factor, write it in terms of phi, and they would have the other person's prior. So if they're both following the same rule, then that transformation is built into the whole system. Does that make sense? It's just logic. So if I just pick this right here, is my prior, and experimenter 2 or whoever transformed it, and they use some rule to develop their prior, right here we would have the same priors. So that's what's happening. So let's just prove this statement. This is pretty cool. I'll write down the info using just one derivative. So recall, I, write it down like this, I phi is going to be equal to the expectation of the derivative, d phi. So I'm going to write my density in terms, or my likelihood in terms of phi. So I'm just plugging in phi into this. This is just going to be a phi right here. And I've messed it up already. I always do this. The logarithm. Log fx given phi. I'm going to square this thing out. And this expectation is over x given phi, if it's not obvious. That's what it is. So this is what I do to compute this thing right here. So I want to transform this over to theta scale. So I'm going to write down this same thing, g theta is equal to phi right here. So every time I see a phi, I'm going to plug in g theta. I'm just going the other way around. And so I want to just do this. And I'm going to make an intentional mistake. Okay? So I'm just going to say, well, let's just plug that thing in, fx, given theta, right here. And so all I'm doing is I'm taking phi and writing down this thing as just g theta. So I'm just plugging that thing into the equation, just shoving it in there. Pulling out phis, anytime I see a phi, I throw in a g theta. Okay, they're the same thing, so I get to substitute them. And so I just plug this thing in here, and you might write down g theta if you like. It's really just phi. So I'm just writing this down in terms of theta, is how I want to write that. And so this f right here, these aren't the same things exactly. I'm just plugging them in, and it looks a little bit different now. And now I'm going to make a mathematical error, and I'm going to say d theta. I get to change that for free, so I just changed that one for free as well. And I just decide to square this thing out. And I've got an error. That I have no mathematical business substituting this derivative right here. I can change the name of variables, but if I'm going to change the operator, I've got to play by the mathematical rules. And so what do I need right here? I need a d theta d phi. Let me give you the poorest mathematical explanation in the world for this. Boom. Right? I mean, that's at least the syntax that we use. Mathematicians don't like it because this is a limiting process and you're not just substituting it. Saying that, every statistician I ever see or physicist thinks about it like this. If you like to know the nuanced mathematics, we have to be a little bit more careful when we do it. But at least we have the phi down in the bottom and we have something canceling, but this rate is coming together. So we can't quite do that. So saying that, my calculus teacher told me that once upon a time. I never forgot it and said never think about it that way because it's wrong, but it's the way I always do it. And I explain it that way. But anyway, I think you can all appreciate that this little chain rule thing has to go in there. That's just chain rule. This thing's supposed to be positive all the way through. So if you do establish this and do it right, that term will always be positive. And so I'm just going to absolute value it. If you don't like it, I guess that's fine. I'm squaring it anyway. This is just a stretch factor on likelihood. So we can't turn that into a negative function.
Should there be g theta?
Yeah, I mean, it's just the name of this thing. So I'd be taking g inverse this thing and plugging it in right there. But it's the right name. So let me just do the last step right here. This is going to be expectation. You'll see it. It's just the same thing that I wrote down here. You have to be consistent about what you're calling things. And so this is going to be expectation of d theta log fx theta. Remember, the expectation is over x. And so I can just factorize this thing out. D theta d phi squared. And this part right here is I theta. So I do mean it the way that I wrote it down, but if you'd like to substitute that and know what it is and know how to do the calculation, I think that's fine. It's just the same thing we do over here. And we've established what we wanted to establish. I'll let you stare at that proof a little bit more, but it really is just that one line. It's just chain rule.
So shouldn't there be fx given g theta?
I'm pretty good with it. I'm pretty good with it. So, why don't you do it by hand for an example? You'll end up writing down the same thing. You might use slightly different notation when you do it all. But yeah, when I'm writing down this theta right here, I'm writing down G inverse V. When I'm plugging that in, that's how I got there. And so I didn't explicitly use the notation G. I can substitute back and forth just like I did right here. So it's just a question of what am I calling theta? So I'm calling it what it is. I'm assuming everything is invertible so that I can make this all very swift. If you're transforming functions that are not one-to-one, it's kind of hard to go back and forth and have the conversation. And so if you are going to be transforming your scales, you want to probably make sure that you don't tangle everything up one way. So that's Jeffrey's prior. That's what it is. So it has this transform invariant property just kind of built into it. That's all very nice. We like transformation invariance because it means that if we follow this prescribed rule, it doesn't matter how we think about the parameter. Now, I will point out in statistics, we usually aren't given the model either. And so lots of considerations have to be made. So this is assuming you've got the same model and you agree on the data generating functions. It's just a statement about, given that, now I can induce a prior so that even if we didn't talk to each other and we both use this rule, we'd come up with the same analyses. And I think that that's appealing, and that's what Jeffrey's wanted to do. So let me give you another transformation invariant rule. I wrote it down a little bit more generally last time. I just want to make a point with this. I'm not saying this is good. So here's another transform invariant prior. And I'll take the worst one I can think of. In my class of priors, I usually call this Scotland's prior. So this is my totally not rational prior. I feel no obligation. So this is going to be proportional to expectation. I'll say d theta fx given theta. I'm going to take the logarithm right here, just as I did before. And instead of squaring this and then half powering it, and I could cube it up and third power it, making sure to take care of the sign. You know, in this, you could end up taking, just because the way the chain rule works out, when you take these derivatives right here, second derivatives, really get pulled out into squares. It's because it's a homomorphism, right, Dan? So we learned this property a long time ago about determinants. Still can't forget it. I thought it was all very cool how you could end up manipulating these determinants very easily. But anyway, so I'm just not powering this thing up, and I could have powered it up and taken some root power on the outside. But what's wrong with this prior? This is transform invariant. It's got all the right properties, right? So if I ended up substituting in d phi right here, and I change that variable, and then I put that other stretch factor right here, there would just be one of them, and it ends up sliding right out. It doesn't get squared. And so this is transform invariant too. What's wrong with this prior? Would you use it? Same thing. X. Same thing. These are all vectors.
Are you going to have issues with things being negative?
Maybe. So I don't think so though. So I think in this case it ends up working out just real nice that I just missed being negative. Get real close though. What does that mean? It's pretty small. Absolute value of this thing is pretty small. So remember what I was saying in all of this, that if I can do Fubini's right here, and if you end up taking a standard distribution that you're familiar with and you calculate this, I know what the number is. It's only a few times where I always know what the numbers are. Let's just look at this real quick. So if I take this, well, I'll let you work it out. But this is 0.
Yeah, because it'd be 1 over...
You see this in inference class a lot.
Yeah.
So in that sort of thing where we, if you want to just recall back a couple semesters ago, when we were looking at the Kramer route sort of thing, this was established in there. So I use this fact over and over and over again that this thing is 0. You just work it out, just apply the chain rule, figure this out, write down the density. You'll end up integrating over fx, it'll be 1, and when you take the derivative, you'll be taking a derivative against the constant. And so, kind of a neat thing. So this is 0. Transformation invariant, right? I say 0, you transform 1 to 1, you say 0 too. So what's the probability of 0? So it's not going to lead us to anything constructive in probability land because most stuff won't add up to 1. And so that's kind of a point, is that if we end up placing priors on stuff, we don't want to put 0 mass on things because you can never multiply yourself out of that. What are we multiplying into the prior? We're multiplying in the likelihood. So let me just show you something. And this is kind of cool. I think I'll just show you with a picture. Is that as n gets big, it really doesn't matter which prior you use. So note, if you don't place 0 mass on the truth, so this is some value of theta, right? This is how we're thinking about it. So there's true theta right here. My prior right here, if I did this would be a terrible idea. Don't do this. If you don't place 0 mass on the truth, what's going to happen, I'm going to say n small. What happens is I have something right here. This might be my likelihood function. And then maybe I have some prior right in here. And so let's just pick my prior to be something that looks like this. This prior would perform pretty good because it's at least placing mass where the likelihood is starting to place mass. And so this is what might happen if n is small. This is a function of n right here. And as n gets big, the prior doesn't change. So as n is big, my prior is going to stay the same. So I'll just write it like that again. In the likelihood function, we'll start to peak. And this is a function of n. And so really, don't place 0 mass on truths. Don't put 0 mass anywhere. And so unless you're restricting that part of the parameter space. So yeah, we put 0 mass on the precision being negative because that's not permitted. You know that it can't. So that's the only time you ever want to place 0 mass is when it's outside of the parameter range. And so even if we did all of this stuff, all these transform invariant things, even if we chose different rules to come up with our priors, if n is big, we'll probably agree with each other. And if n is small, our prior will have a lot of impact. And so this is the same sort of thing that guides that MLEs are consistent. And so posterior estimates are going to converge to maximum likelihood estimates when n is very, very big. Prior doesn't become a factor. And so, but I would say don't do things like this. But what this really tells you is don't place 0 mass, and there must be more to it than just transformation invariance. So let me just state a fact. Fact. And this is just kind of pointing out there's more to it than transform invariance.
In this case, of Jeffrey's prior?
Yeah, so Jeffrey's prior, it's what everybody's using, and people will come up and they'll say, my reason for using it is transform invariance. And it's like, okay, but I could give you other transform invariant priors. I know a construction now on how to do that, just because I know how this chain rule thing works. And Nobody ever uses those priors, especially this one I just monikered Scotland's prior because it's a really terrible choice. It's like definitely and obviously poor choice to make. You don't get any answer out of it, but it is transform invariant. So there must be a little bit more to it. So it turns out Jeffrey's priors are also reference priors. I'm not going to write down the math, but I'll tell you what it means in English this time, and later on in the class, we'll look at some mathematics. I think this is important. In one dimension. So for a one-dimensional problem, it turns out in higher dimensions, this isn't true. So we'll talk about it in just a moment, what everybody ends up doing.
So, excuse me, here whenever you compare, whenever you make edit, okay, this is what becomes, but how does this relate with the fact that the prior having a zero mass over the
But don't use zero mass. So,
how does this relate?
well, okay, let's say I placed my prior right here. And it didn't cover the answer. I'm gonna get a really bad answer out of this. That is, I get more and more n as this thing starts to peak. I can still have zero mass in here. And so that's a bad idea. So all I'm saying is there's more to it than transformation invariance. So here's my argument. I've given you a prior that's obviously terrible, but it's transform invariant. So there must be more to it than transformation invariance, just arguing transform invariance. Now I'm telling you what the other part is. Make sense? So there were a lot of conceptions of how to come up with priors back in the 50s and 60s. There was something called entropy priors, and they kind of worked out nicely, and in a lot of cases, in one-dimensional cases, they kind of agreed with what Jeffries was saying, but they were different. I'm not going to study those in this class, but this one kind of won out over all the other ones. For one, it's easy to compute, at least in one dimension. But it turns out they also have another very cool property. And this can be found in Bernardo and Smith. And I'll probably give you the proof later in class. So if you want to go to their book, they end up proving this in the book. And I thought it was really fantastic when I read this. I was like, oh, that's cool. That's been answering my year-old question of, there's got to be more to it than just transform invariance and just ease of calculation. But what this actually means is the posterior pulls away from the prior. Optimally fast. As a function of the data size. It's a function of n. So in some sense, what this means is your prior is minimally impacting everything. And so just going back to this picture right here, is the posterior is converging to something. In this picture that we just redrew with zero mass right here, this is not going to converge to the truth. And my posterior isn't going to be able to pull away from my prior, especially that hump in there. My prior is determining that zero mass thing. My posterior can't yank away from it. Multiplying by zeros you can never fix. And so I don't care how big the number is, you're never going to be able to fix it. And so this sort of clunky prior is like optimally slow. I don't know if that's true, but Scotland's prior definitely is. So that thing's optimally slow. You're never going to pull away from the prior. And so we'll talk about this later, but there's a limit and this distance function calculation, and we have to integrate over the whole space. So it's a little bit complicated to do the math. And there's books on what reference priors are, and I go to those books quite often and I look up which prior should I be using. And somebody else has done the math for me. So let me give you an example. Let's talk about logistic regression. Okay, So it's this nonlinear thing. And if you don't know what it is, it's okay, but there's a whole bunch of regression coefficients, and they're all nonlinearly related to each other. So yeah, I'm plugging a linear equation into something that's nonlinear, so it's nonlinear. Let's say I transform all those betas. So maybe I want the ratios of some betas. Maybe I have a reason to do that. Maybe some of the covariates are related to each other. I want to measure the relationship through their measured parameter estimates. So I want to transform these things, and I want to be transform invariant. So then I go after Jeffrey's prior. It's a hard thing to work out. There's a Jazza paper on it. Came out maybe a decade ago. And so I've used that prior. And I've also kind of thought, well, what if I don't want to use those priors? You know, what if I can't work that thing out? Then what do? Well, maybe I work through everything marginally, and I do the one-dimensional calculation, and I just product everything together. And that's what a lot of people end up doing. So let me show you that example that we've been playing around with. Note. So note. And again, let's just do x normal mu phi. It's 1 over sigma squared. And so what do we normally pick for this? Product 1, or proportional to 1, and phi maybe proportional to 1 over phi. These things are marginally Jeffreys. It turns out that if you ended up working out the joint Jeffreys prior, it's not the product of those two things. And so, but people end up doing this all the time. So it turns out in high dimensional examples, more than one, you can't have it all. I can't have this optimal rate of pulling away from everything, and I can't have transformation and variance simultaneously. I have to choose. And so, and that's, anybody that's worked with high dimensional anything knows they have to make choices. And high D spaces are a lot weirder than one-dimensional spaces. What do 1D spaces do for us very well that other spaces don't? They order things. And so it keeps everything nice and tidy. But in high D space, it's very sparse and it's not ordered. And so it turns out you can't have it all. So what people end up doing, so I'll say these are marginally Jeffreys, and they're marginally referenced. So I kind of like that. If I just think about the parameters marginally, and most humans do, maybe this is good enough for me. And so maybe I can just kind of wing it and product these things together. Now some people don't like that. They want to have it all, and you just can't. And so you have to make choices. So what I usually recommend when you're at this like pitfall and it's like, do I want high dimensional transformation or invariant, or do I want something closer to marginal reference? Usually most people would probably choose marginal reference because it's easier to compute. And when you're illustrating the parameters marginally after integrating everything out, it has good properties, at least in the marginal space. I guess that's okay. And so if that troubles you, here's what I recommend doing. Do it both ways. So use the product of Jeffreys priors and use the joint Jeffreys prior. It's a harder calculation. So that information that we get is now a matrix. So we're taking a determinant over the matrix and half powering that thing. And so, and if you get two totally different answers, well, I'm going to suggest you don't have enough data to really answer the question, or you need to think harder about it. And so that's kind of the engineering approach to all of this. Just do the sensitivity analysis. Change some stuff around. So a paper that I had written once upon a time, I had ended up using on my regression coefficients flat priors on everything. So logistic regression looks like this. You end up having this logit function, so PIs are going to be equal to e to the xi transpose beta. This is just a vector of covariance, 1 plus e to the transpose e to the xi transpose beta. And so, and then what you end up doing is you end up looking at these PIs right here, and I'll write down, these are a function of all of your x's and your betas, just to be clear about this. So this is x beta. And what you end up looking at, 1 minus pi x beta, and I end up powering this to the yi, or the 1 minus yi, right here, where your yi's are elements of the 0 or 1. So this is just logistic regression, that binary sort of regression. If you've never seen it before, all you need to pay attention to is, if I plug this thing into this big product, it's something crazy. And so what I was arguing in this applied paper that I was doing, well, this is a linear shift parameter in terms of the x's. Maybe when I transform the whole thing, maybe it doesn't matter that I use something that was behaving as a linear shift, even though I'm not even going to think about the parameter that way. I'm going to transform it to p, something totally nonlinear. And so somebody came in and said, why did you pick flat priors for all of your betas? Pick something else. And they didn't give me any suggestions, so I thought, I don't know what to do, and maybe it did make a difference, you know? And so I went off to the Jazz paper, coded up the whole Jeffreys prior thing, did all my transforms, compared the analyses, and they were really close to each other. And so felt pretty good about that. But there was that concern that if my prior was having a big influence on my analysis, it wouldn't be any good. And so we have theoretical tools now that give us some properties, but in high D spaces, we have to choose what we want. In one-dimensional spaces, this Jeffreys thing is reference. Turns out some of the reference priors, like the beta half-half for the binomial problem, when we're inferring P, that has optimal coverage properties, which is really awesome. Turns out this doesn't guarantee optimality in coverage, but in some problems you get it. And we've seen a couple of those problems. And so really it's entertain a lot of different priors, build them up for your convenience, but then do something mathematically a little bit more sophisticated. If you get totally different answers, you need to pause. That's my best recommendation. So there's a lot of different types of priors out there, and they all seem to limit to this prior right here, at least in one-dimensional space. So it is the default that most statisticians go running for.
So prior D, Jeffreys prior remains a reference prior, but does it remain transform invariant?
And Jeffreys prior is always transform invariant by its construction, by that one line of math.
Yeah,
It won't be reference.
But in 2D, you told us that if we do the product, then it's marginally transform invariant, but it's not transform.
Finally,
Yeah,
that's right.
okay.
So it's not two-dimensionally transform invariant. You have to build that in. So Jeffreys prior can be used that way. And I'll point out, I rarely ever see anybody do it. And so I'm just being honest with you. Go scour the literature, and most people don't do it. But if somebody asks you to really show that your priors aren't influencing all your answers, and that's where you're getting everything from, it's a choice that you can run off to. There's other choices as well. And so saying that, I've pretty much shown you what most people do. What most people do is product marginal Jeffreys priors together and hope that it all works out. And so as just adding a little bit more than hope is they check. And so they change some of their assumptions and see if it changes everything. We're going to see cases in this class where your prior has amazing influence. And so I'll point out a case. We haven't done any of this yet, but in hypothesis testing, there's a famous problem. And so we've kind of learned that for mu in a normal distribution, flat prior seems to be a good choice. Turns out if you use that prior in hypothesis testing, the sharp null hypothesis, if you use it on your alternative space, you get an answer that is totally nonsensical. And so if you guys remember, those of you that go to colloquium in the statistics department, there was somebody here at George that was talking about it, and he said that he just hates that. And that's just such a philosophical quandary. I'm going to explain to you why that happens, and it's not a philosophical quandary, it's just math. But we have to understand all the repercussions of our decisions. So lots more discussion to be had, but ultimately, you guys are ready to go. So get your models, you can work out some priors, you've got some choices, and you've got reasons for those choices. And so you can start doing analyses now. So you're going to get cases where you build up high-dimensional models, and you have no idea, okay, I wrote this thing down, and it's this crazy product, and this has the shape that Scotland's talking about. That's the posterior shape, but I have no idea how to compute where the mass is. And so later on in this class, I'm going to show you how to do all the computation. So we've got a paradigm. It seems nice. It seems to yield good properties. And we need to know how to exploit this in modern problems. So that's where we're going. Does anybody have anything in this class that they really want to study, since we're going to be re-engineering this just a little bit? Anybody hear of anything in Bayes land that you're just dying to know about? Dirichlet processes. Yeah, I was thinking about that. I never attempted that in this class. And so maybe so. So all the semi-parametric stuff that people are playing around with. So Dirichlet processes are basically infinite mixtures of some model. So it could be for clustering or something like that, but the infinite mixture component says you don't have to lock down how many components you think there are, how many clusters there are. So like in a k-means algorithm, you have to specify k. So Dirichlet processes are a process-driven prior. I can't actually write it down mathematically on the board, but I can tell you how to compute it, you know, in some sort of a loop or something. So I can give you a process for dealing with it, but I can't write down, you know, mathematically, characteristically, in closed analytical form what this thing is. So it's a good choice. Yeah, maybe we can, because I think I can. It's actually pretty easy. So if you read through the papers, it looks really hard. And people talk a lot about measure theory and stuff like that, and you're like, what the heck is all this? And so distributions over distributions, now I'm really confused. So I think what I could do is just show you what the algorithm is and show you how to compute it. And so it turns out if you can compute your posterior predictives, coding it up is trivial, but there's some issues. So yeah, that's a good one. Anybody else?
Variation inference?
Variational inference, yeah, maybe that's a really good one too. Yeah, so variational inference in just a nutshell is coming up with this variational approximation. It's a nice fancy physics-based terminology for saying that I come up with an approximate model. It gives you some structure on how to do that. And that approximate model is going to minimize the distance in a Kohlbach-Leibler sense. That function always comes up because it's smooth enough to do math on. And so, but you come up with this approximate model that's easier to work with than your other model, and you run EM on it. And that's all it is. So the whole variational algorithm is EM on an approximate distribution.
What is that?
So expectation maximization. And so I would probably have to build a class in on that if we're going to do it. And those of you that have taken my inference class know it took me a whole week to explain that algorithm. So I'll think about it maybe as a supplemental, but if you didn't know EM, that makes things harder. So, but it's a way of maximizing parameter spaces. It's a cool algorithm. Who knows it? EM. 1, 2, 3. There's a couple people in here that have taken my classes before, and they're even reluctant to answer. Right, Tessa? Like,
I just need to study.
right. I know it, but I have no idea what it is. I remember being pained by this for a week. But anyway, there are a lot of cool things that Bayesians are doing, so let's see if we can get that built into the class. Okay, homework assignment, check your calendars for the midterm, and you'll get something on the schedule soon. Thanks, guys.